So today, since it's the last class, I have only one design example that I want to discuss with you guys from the textbook, and then I can just answer any questions that you may have. So let's go ahead and look at one of the design examples. So this example actually in the book, it started in chapter number 2, and then it kind of continued in chapter number 8 in the context of frequency design. So basically, in this design example, we have to explore the parameters of a controller to control a photovoltaic generator to yield maximum power, as the output of the generator is varying due to sunlight, which is varying, temperature, which is varying, and the load that is connected to the generator. So a general block diagram is shown here. You have a controller, and then you have the process, which is basically your photovoltaic generator plant. And where's my pen? And the photovoltaic generator plant, or the process, basically, it is comprised of 3 different items. You have the power control circuit. You have the actual cell, photovoltaic generator, that is producing your energy in the presence of sunlight. And then you have the current transducer that is going to basically change the value of current from one form to the other form. The output is the voltage coming out of the system, and this voltage is going to be compared with a reference voltage, which is the desired value of the voltage. So to increase the overall efficiency of photovoltaic generator, of course, we are creating a feedback control system, and we want to maximize the power output, again, in the presence of the parameters that are changing. What will be the maximum output when those parameters are changing? So of course, we'll have to change the controller parameters in order to change the power control circuit that you have that is controlling the cells, in order to extract the maximum power from the photovoltaic generator. So this circuit is called the maximum power point tracking circuit. And certain values of current voltages associated with the solar cells that are required for the maximum power output. If you remember from the basic discussion of your circuits class, that whenever you have a resistor and then you want to dissipate the maximum power, then you create a Thevenin equivalent circuit, and your Thevenin resistance should be equal to the load resistance in order for the power supply to supply the maximum power to the load resistor. So kind of similar concept over here. But in this case, of course, you have the variable load connected to your generator, photovoltaic generator. You have temperature that is changing, which also changes the power output of the photovoltaic generator. And on top of that, of course, you have variable sunlight. Throughout the day, the sun changes direction, and the light on the photovoltaic cells are going to vary as well. So in the presence of all these components, how you can extract the maximum power from the photovoltaic generator. So the maximum power point tracking circuit, it uses closed loop feedback control to seek the optimal point to allow the power converter. Of course, power converter is this circuit right here, power circuit, to extract the maximum power from the photovoltaic generator system. Now this circuit is an active, it's comprised of an active filter. It's comprised of, not a filter, but basically it has active elements in general. So it may have your integrated circuits, your operation amplifiers, and some of them we're going to study, of course, in the next semester. Some stuff that we're discussing here, we're going to study in next semester as how to create those circuits that we are going to study here in terms of block diagram. So the block diagram that we just discussed, you have two transfer functions. Of course, you have the transfer function of, you have the transfer function of your controller, and then you have the transfer function of the plant that we can and that plant is simply GS. This whole thing is simply GS. So you have GCS, GS, our usual control system. So for the and that GS, of course, power circuit, photovoltaic generator, and current transducer, we are taking it as a single block diagram. So these values are given in the example in the textbook. For photovoltaic generator, if it has 182 cells that are generating over 1,100 watts of power, value of K is about 300,000, and the value of the pole is 360. So these values are given to us. You have to calculate the value of Kc, the controller gain, and the two time constants, T1 and T2. In fact, T2 is the time constant of the circuit. Since it's a pole, T1 is, or tau1, sorry, tau1, of course, is one of the zeros. So the controller shown is called either a lead compensator or lag compensator, based upon the values of the two time constants. Again, what are lead and lag? I'm going to discuss in a little bit. So what is the primary goal? The goal of the controller design is to minimize the effects of the disturbance and plant changes. So remember, in the plants, few things are changing, which are the sunlight, your temperature, and your load. And of course, you can have external disturbance to the system as well. So to minimize their effect, we want a high gain at low frequencies. And we also want to reject the measurement noise. And to do that, we want a low gain at high frequencies. So these two things we are looking for. Again, we are trying to relate it with the frequency domain. So the gain of the controller circuit has to be high at low frequencies and low at high frequencies. And we have these parameters. That is the loop gain, not just the controller, but the loop gain. The loop gain, which is GCS, GS. So this is your loop right here, closed loop, GCS times GS times 1, because it's a unity feedback loop. So the loop gain has to be greater or equal to 20 decibel at low frequencies, less than 10 radian per second, equal or less than 10 radian per second. And the loop gain has to be less than negative 20 decibel, that is less than 1. Negative, anytime you have negative decibel gain, that means the actual gain is less than 1. Gain of 1, of course, is 0 decibel. All the positive gains are more than 1. And all the negative values of gains are less than 1, which is also called attenuation. So at high frequency, greater or equal to 1000 radian per second, we want attenuation, or the gain is supposed to be less than or equal to negative 20 decibel. And the third parameter that we never discussed, and we're going to introduce it, is the phase margin. Phase margin has to be greater or equal to 60 degrees. So what is phase margin? Phase margin is a measure of the stability of the control system, one of the measures of the stability of the control system. It is measured from the Bode plot as the difference of the phase at the frequency, where gain of the system is 0 decibel, and negative 180 degrees. So we are taking the difference of the phase at the frequency where gain of the system is 0 decibels. So we will observe the phase of the system at the frequency where the magnitude gain is 0 decibel. And we are going to subtract negative 180 degrees from that. So that difference is called the phase margin. The higher the value of that phase margin, the more stable the system is. Now the frequency where the gain of the system is 0 decibel is called crossover frequency. And you can observe that crossover frequency, of course, in the Bode plot. And likewise, you can observe the value of the phase at the crossover frequency from the phase Bode plot as well. And that's what we are going to do. So we are going to plot the magnitude and phase Bode plot first for the uncompensated system. Uncompensated system means that you are not doing any compensation. So your controller gain is 1 initially. And we are going to plot the Bode plot, magnitude, and the phase to observe what is the magnitude of the phase, magnitude of the Bode plot at 10 radian per second if it is greater or equal to 20 decibel, at 1000 radian per second if it is less or equal to negative 20 decibel, and we are going to observe the phase margin. And we're going to do that to see what compensation is required from the controller in the control system. So let me go to, so I created this plot using the Bode function. So this is exact Bode plot, it's not approximate. Remember, Bode plot is approximate. All the approximation that we have learned, that is used in Bode plot. Now the Bode function in MATLAB, it does the exact Bode plot. That is, it takes 20 log, whatever, 1 plus whatever, and then change the value of omega, and then plot the exact Bode plot. That's why you see clean curves over here, but not sudden changes that we have in approximate Bode plot. So anyways, I plotted GS, which is this K over S plus P, GJ omega. So I plotted that using Bode plot. And here we are going to observe three things. The first thing we're going to observe at 10 radian per second, you have approximately close to 40 decibel gain for the uncompensated system. That means compensation for that part is not really necessary. You have very high gain at 10 radian per second. So our first condition is pretty much getting satisfied. It is greater than 20 decibel at 10 radian per second. So you don't really need GCJ omega for that. It's 1 right now. However, the other two conditions, first we're going to observe the crossover frequency. Or actually, first, let's see at 1000 radian per second, the value of gain is negative 11 decibel that I read from the graph. Now, this value is greater than what was required. The value that was required was negative 20 decibel, at least at 1000 radian per second. We are getting negative 11, which is, of course, greater than negative 20 decibel. So we do need compensation at higher frequencies to reduce the value of gain to at least negative 20 decibel. And the third thing is your phase margin. So first, you're going to locate the crossover frequency. So you're going to look at 0 decibel line where it intersects the gain and read that frequency from the magnitude. And that frequency is approximately 500 radian per second from this magnitude plot. And now you're going to look at 500 radian per second 1, 2, 3, 4, 5. So right over here somewhere. And observe what is the phase of your system. So phase of the system, whatever it was coming out to be negative 144 or something like that. I did not put the actual value of the phase. But you can see that this is negative 140. And then at 500, it is a little less than negative 140. So it is negative, approximately it was coming out to be negative 144. So the phase margin is 36 degrees, which is negative 144 minus negative 180. Because the minimum value of the phase is negative 180. So that's your phase margin, 36 degrees at the crossover frequency. This phase margin is less than what is required, which was at least 60 degrees at the crossover frequency. Now, the crossover frequency can change if you change the parameters of the controller, GC, J omega, as you will see. But whatever the crossover frequency is going to be, your requirement is that at your phase margin has to be greater than or equal to at least 60 degrees. So that means we need two things. We need to reduce the gain at high frequency. Let me reduce my zoom. Okay. So the controller must further reduce the gain to meet the high frequency requirement, because we need negative 20 decibel at least. And we need the compensation circuit, the controller circuit must increase the gain margin by at least 24 degrees. So since it has to increase the gain margin by 24 degrees, that circuit is called the phase lead circuit. That it is leading the phase at the output with respect to the input. And this is one of the circuits that we are going to discuss in linear integrated circuits. How to create phase lead and phase lag circuits using operation amplifier, such that you can change the phase of the output for that circuit with respect to its input. Either you can lead either the output phase is going to be greater than the input phase, which is the phase lead circuit, or the output phase is going to be less than the input phase, which is the phase lag circuit. So that's one of the circuits that we are going to look at, as I said, in integrated circuits class. If you're taking that class next semester, then we're going to discuss those circuits. But we need a phase lead circuit for our controller to increase the phase margin by at least 24 degrees. Because we already have 36 degrees. And remember, when you're calculating, when you have GC, J omega, and GJ omega, and you're calculating the phase, remember the phase is going to be phase of GCJ omega plus phase of GJ omega. When you're calculating a phase of product of complex numbers, then the phase add together. And likewise, when you're calculating the magnitude in decibel, then of course, in decibel, GCJ omega decibel is going to be added to GJ omega in decibel. So if you're not calculating in decibel, of course, that's going to be a product. But once you convert the product into decibel, you multiply 20 log 10 of this, then you can write that down as 20 log 10 of GCJ omega plus 20 log 10 of GJ omega. So that's going to be GCJ omega decibel plus GJ omega decibel. So we need a controller that is going to further reduce the gain at high frequencies, can increase the gain at low frequencies as well, because the requirement has to be greater than 20 decibel. So if you can increase the gain, but one of the requirements that was not satisfied is that high level frequency gain is not small enough. So it has to reduce that gain. So we have to further reduce that gain. When we add GC J omega gain, it will further reduce the gain at high frequencies. And of course, the angle has to be 60 degrees, from 36 degrees to 60. So at least 24 degrees has to be added by GC J omega. So again, in the book, one of the possible transfer function of the controller is given as that the controller gain is 250, tau 1 is 0.04 second, and tau 2 is 100. And again, this is from the textbook that is given. One of the possible configuration of the controller to achieve the given requirement is this. So once we have that, you write down the loop transfer function gain, which will come out to be this 3000 S or 25 S plus 0.1 S plus 360. And when you do the Bode plot, phase and magnitude of this quantity, then of course it's not very hard to do that. I just use the Bode function. And it looks like this. So now if we look at 1000 radian per second, so first we look at 1 radian per second, 10 radian per second, so this is 10 radian per second. At 10 radian per second, your gain is still more than 20 decibel, greater than 20 decibel. So that first condition is satisfied. The crossover frequency, zero line, is somewhere over here. And it was approximately 85 radian per second, 84 point something radian per second, the crossover. So crossover frequency did change from 500 radian per second to 85 radian per second. And at that crossover frequency, we measure the phase margin, which was coming out to be 61.5 degrees approximately. So this was approximately negative 119 or something. As you can see, this is negative 120. So the value over here was approximately negative 119.5 or something, which will be subtracted, or negative 180 will be subtracted from that value. So that was negative 119, if I remember correctly, 0.5 minus negative 180. So it was approximately 61.5 degrees, or 60.5 degrees rather. 60.5, not 60, 60.5 degrees. So that also satisfies the phase margin condition. And finally, if you look at 1000 radian per second, our gain was supposed to be less than negative 20 decibel. And at that time, the gain value is approximately negative 31 decibel. So this transfer function for the controller does satisfy all three conditions. And again, I did not design this. Again, I just picked up what is given in the book, but I elaborated on how they're reading everything in the book. They're not really explaining properly about these graphs as how they're reading the phase margin or anything. So I just elaborated on that to show you that by adding that and plotting the Bode plot, now from the Bode plot, you can read clearly as what is the gain requirement, if it satisfies or not, at the crossover frequency, the phase margin, does it satisfy or not? And of course, at the low level frequency, does the gain satisfy or not? In this condition, all three conditions have been satisfied. Therefore, this is a valid, this may not be the only controller parameters, but this is one set of valid controller parameters. The last thing is you can check the step response as well for the system to see if it's not going crazy, it's settling in a proper amount of time and peak overshoot is not extremely high. So in this case, peak overshoot is about 19.5%. It is settling down, of course, as you can see, 1 with the step response. So the steady state value is 1 for the output. And settling time, as you can see, is settled down to 1 between 0.1, 0.15 seconds. So whatever is the settling time condition, remember settling time condition was supposed to be what, like 4-time constant or 5-time constant. So I did not calculate the time constant of the circuit. You can easily calculate the time constant of the circuit when you take the roots of the denominator. And you can see which value of the root is closer to the 0 axis. That is going to take longer to settle down, and that will be your dominant root. So when we do that, we can check what is the time constant of the circuit. But from the graph, we can see that it settled down pretty much to the steady state value between 0.1 second and 0.15 seconds. So the time constant is somewhere in between. I just put the center value, 0.125 seconds. But it can be smaller than that, of course, based on what is the value of 4 time constants. So the step response also is not taking very long to settle down. Peak overshoot is okay, about 20%. Could be lower, but 20% is all right. And yeah, settling time is not that. It's like 125 milliseconds. It's not that bad. So this is one of the examples in chapter number 8. It started in chapter number 2, and I thought it was a very interesting example. So I thought I should discuss it with you. All these, of course, I use. This is the step function in MATLAB that I use. Of course, Bode function in MATLAB that I use to plot these. And the values, of course, are coming from the book, although I elaborated on these, but this is not in the book. But yeah, so this is one of the examples that is using the frequency domain Bode plot to specifically show as how you're going to observe values from the Bode plot to design the gain of the controller and stuff. Of course, we did not specifically design it. We just took it what is given in the book, but based on that, we did observe the values from the Bode plot.